Okay, so we are at the end of the planned lectures for the semester. So what we've got left is a set of other topics that I wanted to make sure that we covered, as well as a couple of requested topics. So we've got 5 lectures left today, and then 4 more up through the 21st. The 22nd is the official end of this semester. So we've got those 5 lectures to work with. One of the things I want to talk about is Xcode tools. Specifically, I want to talk about Interface Builder and how you use Interface Builder with Swift programs. So I believe that's what I'm going to be lecturing on next lecture. In addition to Interface Builder, I also want to talk about Instruments, which is the performance tool that Apple provides for finding hotspots in your program, examining, essentially running programs and having analyses on those programs. As well as talk about a few other pieces of Xcode and essentially close out the Apple technologies that are involved with Xcode. And I want to talk more about barycentric coordinates because many people over the last 2 lectures asked Kevin to talk more about that, and he didn't have time to. So I'm going to cover that today. We'll talk more about what barycentric coordinates are and essentially a grab bag of other OpenGL concepts, with the desire to give you a place to continue to follow the line of logic that we've had in class if you're interested in doing additional 3-dimensional game programming. So moving from 2-dimensional programs to 2.5D programs and full 3D programs, and utilizing OpenGL or Vulkan or Metal or DirectX as a rendering library. We just have some additional math concepts to discuss. So if I'm going to talk about barycentric coordinates and the math behind those, I'm going to introduce the other math concepts from 3-dimensional graphics, because it defines a lot of what's going on mobile right now. So that's our example today, and I'll be done with OpenGL after this lecture. The last 3 lectures, I kind of want to do requested topics. Several students have requested topics that I talk about for this semester. I haven't decided if I'm just going to go ahead with the topics that they've been asking for, or if I should do a survey and have you guys decide what those topics are. We'll do that next time. Either say what those topics are or actually have a survey and see what topics are there. So if you have interest in a particular topic, just go ahead and send me an email between now and Wednesday. If I get enough emails that say talk about this, talk about this, talk about this, I'll just talk about that. So what are you interested in? Let me know. So that's our plan. So the title of this lecture is OpenGL ES 3D, but it actually has more to do than just how to use OpenGL with 3-dimensional data. So let's start with math background of vectors. I am not a mathy guy. I am a kindergartner. I like crayons. I like things I can see. If I can't see it, I have a hard time figuring out how it works. That's me. But there are some math types, usually on that other side of campus where people do math things, where they have a bunch of equations and they go blah, 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 and write the solution, and you're done. Look how simple it was. And that's like all of math. I just think, no, it doesn't work that way. Theorem proving, all those kinds of things. I think it's great to not be facetious. Like the concepts that are introduced in those math classes are very powerful concepts, but they're difficult. I appreciate mathematics for what it does specifically in the field of geometry. How can I use math to draw something? In 4th, 5th, 6th, 7th grade, whenever you started doing it, graphing an equation was a really good thing. Probably not 4th grade, but graphs made sense to me. And I think it makes sense to most people. Not all people, certainly. But most people, when they see graphs of values, they now get a feeling for what math can be used for. So graphics is a very natural extension of this. How can I use mathematics in order to draw environments? How can I create things of value that are of use not only in entertainment, like for games, but also for scientific visualization and those kinds of topics? A lot of what graphics APIs are used for is just visualization of data. So understanding math concepts and how they apply to geometry is of interest. So let's look at some vector operations and how they are used from a geometric point of view. So for example, vector addition and subtraction. If you have two vectors, A and B, and draw them, they have a magnitude and a direction. Vectors from the math point of view are just a set of numbers. You have a vector of dimensionality 4, it has 4 numbers, you can do some things with that vector. But when you apply it to geometry, you can see that thing. You're graphing it, and the graph itself is actually the thing of interest. So just the vector itself, having magnitude and direction, I can use for different things. A vector is always magnitude and direction, but if I say this vector represents a position in space, it's a point, now that vector has a geometric meaning. The tail goes at the origin somewhere in the space, and then the value of the vector says where a thing is in space. So this bag, relative to that origin, has a vector between it. So that's the geometric understanding of what the vector is. That magnitude and direction has a meaning. The addition of two vectors also has a meaning. If I have a vector A and I think of it as a point vector, and I have a vector B, which is also a point vector, or a vector that represents a point, the vector A plus B gives me a third point that means something. The addition is actually not the most useful, though. The most interesting one is that subtraction. If I have two vectors, A and B, and they represent the positions of two things, say a tank and its target, I can subtract B from A, and that gives me the vector that goes from B to A. Tells me what direction I need to point my turret to blow that thing up. That's way better than just A.x minus B.x, A.y minus B.y. It means something. So this is one of the simplest vector expressions, but what it is, if you gave it a name in code, is vector between. If I have a vector A and I pass it in as the first parameter, and a vector B is the second parameter, I would name that function vector between, and it would give me the vector that goes from B to A. That's subtraction. And this is all kinds of useful. Use it for a lot of different things in graphics. Positioning of cameras, finding out velocity vectors to be able to get you from point A to point B. And you use this not only for drawing things, but also for vehicle control, for lots and lots of stuff. So vectors are this very general purpose, drag it through the mud and it still works type math concept that we use all over the place in graphics and other places. So subtraction. That if you subtract B from A, so A minus B, it gives you a vector from B to A. So you kind of read it backwards. The vector goes from the second thing to the first thing. Scalar multiplication also has an interesting meaning and understanding, especially when you talk about the fact that a vector is magnitude and direction. So if a vector is magnitude and direction, how come the field values for most vectors is x, y, z, or x, y? I don't have vector dot magnitude or vector dot direction? I thought vectors were magnitude and direction. Well, that's because directly storing the vector's magnitude and direction is dependent on the coordinate system in which the vector exists. If it's a vector in a spherical coordinate system, a canonical coordinate system, some non-Cartesian coordinate system, you can still represent magnitude and direction. So you can think of it as a computed property. If I ask a vector for its magnitude, it takes x, y, and z and computes the magnitude from them. But it is just as much a property of the vector as vector.x is. So the magnitude of a vector is the square of the components square rooted, right? Well, scalar multiplication allows me to modify just the magnitude of the vector. So if I have a vector that goes in a particular direction and I want a vector that's twice as long, I apply scalar multiplication. What's the geometric representation? It makes the vector longer. I can actually see that the vector gets twice as long. What does that mean for non-positional things? When you have a vector that represents a velocity, if you take the scalar multiplication by 2, it goes twice as fast. So that's an important concept to draw. I know these are fairly surface concepts, but think about them this way. Think about the geometric meaning of the numbers. Also, what scalar multiplication allows you to do is if you multiply by the inverse of the magnitude of a vector, 1 over its magnitude, as a scalar multiple, that gives you a vector that just has direction. It's going to be a vector of length 1. If the vector happens to have length 1, great. But a vector of length 1 is how you say the direction of a vector. So these are referred to as unit vectors. So a lot of the inputs to geometric functions will assume unit vectors as the input. So only vectors of length 1 work. So that's scalar multiplication as well as normalization of a vector, coming up with the vector's normalized form, its length 1 form. So you remove its magnitude component and just deal with its direction. Why this is particularly useful is when you get to dot products and cross products. You can't multiply two vectors together. There's no such operation. It just doesn't make sense. But you can take the dot product and the cross product. The dot product is a really odd thing. You take in two vectors and you get out a thing that is not a vector. You get a number. So put 2 oranges into the machine and I get out an apple. You are getting a thing that is of different nature. But what the dot product does is it tells you how much one vector is like another. And in particular, if the two vectors are unit vectors, it tells you something interesting. But the dot product itself is defined as magnitude of A times magnitude of B times the cosine of the angle between them, whether these are 2-dimensional vectors or 3-dimensional vectors or 4-dimensional vectors. Dot product works on all those different dimensionalities. So if you imagine 1-dimensional vectors, the dot product is multiplication. Interesting. But for 2-dimensional vectors here, you can think of it this way. This length of A, length of B cosine thing may or may not be useful to you. But if A and B both happen to have a length of 1, where both are just talking about their direction, now it's just the cosine of the angle between them. Cosine, when you're talking about vectors, is going to be a number between 0 and 1. If they are oriented opposite from one another, you'll get negative values, but you can still take the absolute value of that and still get a number between 0 and 1. This is percent like. If I take A dot B, I can find out how much A is like B as a number between 0 and 1. Why is this useful? Well, it allows you to know if two things are going in the same direction. If A and B are both velocity vectors, and I take the dot product of their normalized versions, it tells me how much two objects are going in the same direction. I can also use it for lighting. If I take the dot product of the normal, or the direction out on a surface, with a light, it allows me to know how directly the light is incident on an object. So dot product all by itself is a lighting calculation. So use dot product for lots of things like this. How much two vectors are like one another. If it's 0, they're exactly perpendicular. If it's 1, they are the same vector. If it's 0.5, there's 45 degrees between them. So that's what dot product tells you geometrically. Cross product is a situation where I put in 2 oranges and I get out an orange. It's 2 vectors going into the operation and a vector coming out. However, cross product is only defined on 3-dimensional vectors. And the reason why is because the cross product is defined as length of A times length of B times the sine of the angle between them times n, where n is a vector that is perpendicular to both A and B. Why is it this? Ask the mathy guys. All I know is that it's really downright useful. If I have 2 vectors, A and B, I can find out a third vector that is exactly perpendicular to both of them. This is really useful for finding what way is out from a surface. So if 2 people are running along the ground, I can take their velocity vectors and I can find out which way is up, even if they're running uphill. So that's really useful. So again, this is most useful when A and B are unit vectors. So I can ignore the size of A, size of B sign junk, and I just get a vector n, whose length is 1 and is perpendicular to A and B. So this doesn't work for 2 dimensions, right? Because I can't get a vector that is perpendicular to A and B if I can't go out of the page. So cross product only works in 3D. So that's a really common operation to need in 3-dimensional graphics. So with these, we introduce the concept of point vectors and free vectors. There's no difference between a point vector and a free vector from the point of view of the numbers. It's only the way you think of them. Point vectors are positions of things in space where the vector's tail is the origin, the vector's head is where the object is. Free vectors have to do with one thing related to another. So the velocity of an object would be a free vector. So a lot of times in documentation about graphics and about the movement of objects, you'll have things referred to as point vectors and free vectors. So how does this relate to graphics, as we've been discussing the last few days? Well, moving of objects around obviously is useful with vectors. But we can actually use vectors directly in the rasterization process. How do I take a definition for 3 points that define a triangle and create a bridge between the 3-dimensional world and the 2-dimensional world? Take a 3-dimensional triangle and render it in 2 dimensions. Because the job is we have this array of numbers, and we define where those 3 points relate to that array of numbers, and then I have to fill in all of the array of numbers. So I have an array of 100 by 100 numbers, and I apply some arbitrary mapping from a coordinate system to that, either 0 to 100 or 0 to 1 or 0 to 1,000,000. That tells me where those 3 points end up in the array. And I have to decide which pixels get filled. So there are several ways to accomplish this. You can use a line drawing algorithm and find out which side of the line different pixels are on. That's one way of approaching this. There are a few others. There's actually one that's very straightforward and is going to give me some more really interesting, tasty data as a side effect. To get there, let's build up to it. Here's an interesting idea. So we have scalar multiplication on a vector. We have some vector A, and that defines a point. And I have an origin. So if you think of A as being somewhere on a map, and I want to go from the origin of the map over to A, which is a point of interest, say I want to go and find dinosaur bones or whatever there, I walk a path that is a direct path from the origin where I'm starting over to A. And I define scalar multiples of A to say what points there are as I walk there, as I take the time to get there. So 0.25A, 0.75A, and 1A. So I'm 1/4 of the way there, 3/4 of the way there, 100% of the way there. Again, mapping to this number between 0 and 1 allows me to say I'm walking from here to there, and this is my completion to getting there. So small distinction, but important one. I can also do this. I can actually go beyond A. I can say I got to A, and I kept going in the same direction. So at 125% of the way, I ended up here. And I can go negative. I can say before I got to the origin point where I started counting, I was still walking in the same direction. So these also have a relation to this path. So fairly straightforward. Just wanted to bring this to mind. What if I have another point B? And this point B has all those same abilities to walk to this other point of interest. I had some dinosaur bones at A, and I had some mammoth bones at B. We can define a third point of interest that somehow has a relation to points A and B. And this is where our analogy of where the bones kind of breaks down. I guess you could say you have some pirate riddle and the X marks the spot where the two things cross, whatever. I'm throwing away the analogy at this point. You have A plus B, which defines the third point. But I can still take scale multiples of this. So I can say 3/4 of the way along A, start walking in the direction of B. So start walking along here, and then once I get 3/4 of the way there, I start walking in the direction that I would walk in order to get to B, in order to get to this point. I could also create scalar multiples of both B and A. And what this does is, it gives me the ability to find locations between A and B as my endpoint. I walk along for A a little bit, and then I walk along B for a little bit, and I get to here. Or I walk along B for a little bit, and then I walk along A for a little bit to get to here. Up to there. So this line of values has a specific relation. Everything on the yellow line is going to be where the scale multiples between A and B add to 1. So I'll only end up on this yellow line if the coefficient of A and the coefficient of B add to 1. So this is referred to as a linear combination of A and B. And it has a geometric meaning. It means that I'm walking along the line between A and B. So now I can treat walking along the line between A and B the same as walking between the origin and A by creating a linear combination. So this is called a blend. What I'm doing is I'm actually blending two values. I have 3/4 of A and 1/4 of B, and that gives me somewhere along this line. It gives me something along the path from A to B. But this only holds true if they add to 1. So this concept of adding to 1 is central to the concept of a blend, of a linear combination. If they don't add to 1, it's not a linear combination. You're just spouting nonsense. So points that are not along this line are not going to add to 1 as well. If I end up at this point up here, the scale multiples of A and B won't be 1. So it's not just if, it's if and only if. So I create these interesting blends. Let's take this concept one further. Now I have A and B and C. And I would like to be able to walk along the lines between A and B and the lines between B and C and the line A to C. Well, I can do that. I use the exact same math. I can walk along B to C by creating linear blends of B and C that add to 1. I can go from C to A by having linear blends from C to A, and A to B and B to C. Anyway, so I can walk along the yellow lines on the triangle. So halfway between those two is 0.5A times 0.5B, and 0 of C. There is 0.5B, 0.5C, and 0 of A. And 0.5 of A, 0.5 of C, 0 of B. This allows me to walk on each one of those lines. Well, you know where I'm going from this. Well, what about the ones that add together? If I take 1/3 of each, that gets me to the middle of the triangle. Any triangle. So I can find the center of any triangle by taking 1/3 multiple of each one of the vectors. That sounds useful. So it doesn't matter what the triangle looks like. A could be any value, B could be any value, and C could be any value. 1/3 multiple linear blend of those three values gives me the point in the middle. So I can create other linear combinations. I can say 10% of C and 10% of B and 80% of A. That gives me a point that's fairly close to A, which makes sense because I'm using most of A in order to get there. Or I can have something like 0.8 of A, 0.5 of B, and 0.3 of C. Notice that 0.8 plus 0.5 plus 0.3 is not 1. This actually gives me a position outside the triangle. So this forms what are called the barycentric coordinates. I use 3 numbers to address locations inside the triangle. And why I do that is because if I say that the 3 linear blends have to add to 1, it tells me just by what those coordinates are if a point is inside the triangle. So everything outside the triangle is when lambda 1 plus lambda 2 plus lambda 3 equal 1, but one of them is negative. Everything inside the triangle, everything must add to 1 and they're all positive. So what this tells me is I can do a very, very easy operation in order to determine whether a pixel is inside the triangle. Is lambda 1 and lambda 2 and lambda 3 positive? Because if they're not, they're going to be outside the triangle. If you had that, it would make rasterizing your triangle a whole lot easier, right? You'd be able to write your fill in the triangle function really quickly. So if you calculate the barycentric coordinates and then just check, are any of them negative, you know whether or not that pixel is inside the triangle. So that's useful, certainly. But in addition to this, not just am I able to find out what's inside the triangle, I can also use this as a mapping. So I can use it to blend things. Remember how we had associated colors with each point on the triangle in your last lecture? Where you had red for one point and green for another point and blue for another point? And you could blend the colors together inside the triangle? Not only does it tell me whether I'm in the triangle, it also tells me how close I am to each one of the points. If I have 80% of A and 10% of B and 10% of C, I know I'm going to be very close to A along a line towards the middle. So that point is going to have a specific set of barycentric coordinates. So this is really useful. So I can also go backwards. I can say not only what is this location with respect to the barycentric coordinates, I can say given a location x, y where a triangle is found, is this in the triangle? So I can go forward and backward. So here's the equation for it. X is equal to some location lambda 1 times x1, which is the x location of A, lambda 2 times x2, which is the x location of B, and lambda 3 times x3, which is the x location of C. And same thing with y. By definition, lambda 1, lambda 2, and lambda 3 add to 1. So I can now start reversing this equation. I know that lambda 3 is going to be equal to 1 minus lambda 1 minus lambda 2 by definition. Otherwise, it's not a barycentric coordinate. I'm just spouting nonsense. I can also solve for x and y. I can do some rearrangement by substituting for lambda 3 and do lots of moving around, and I get this. So now the locations are for what lambda 1, or the values for lambda 1, lambda 2, and lambda 3 are all relative to the input points. So that allows me to convert back and forth between barycentric coordinates and x, y, where the triangle is found. And that lets me do this. So I can take triangles that represent primitives, and I can map things on them. So if I can blend 3 colors, I can also blend 3 texture coordinates. I can find ways to map from some other coordinate system and map on top of a triangle. It's a linear blend of 3 inputs. I can blend 3 colors, I can blend 3 texture coordinates, I can blend 3 normals, I can blend 3, those are the 3 main ones that people do. But there are 3, you can associate any value with the 3 points on the triangle and blend for the elements in the middle. It's a linear combination. You're blending those 3 things together. Texture mapping is just the one that is the most impressive. So that allows us to create really interesting pictures that we can map on top of triangles. Because it doesn't matter what the values of the points for the triangle are. I can map link, and link can be anywhere on the screen. It doesn't matter where the triangles that represent his geometry are. It still maps the same pixels on top. So now I'm not interested in pixels. All I'm interested in are where are the triangles. By moving the triangles, I move the objects. So that leads us to two-dimensional transformations. And how do I move the triangles around? That becomes the point of interest. So just moving back to barycentric coordinates, this set of equations is performed for you by OpenGL. When you run your vertex program and you output GL position for a single vertex, OpenGL takes care of collecting the other two for the triangle and then runs this to find out what the barycentric coordinates are. And that's how it knows what the inputs to the fragment program should be. It does this step for you. You could write this step yourself. If you had a file that gave you positions of triangles in a scene, and you had code that allowed you to output to an image, say to a bitmap image, to a PNG image, to a JPEG, whatever, you could actually do rendering yourself. Given inputs and outputs, you could just write a C program with no dependencies, no libraries other than maybe the standard C library, and write your own software rasterizer. So that's actually what they do in 4600. They teach you how to rasterize triangles with texture mapping and color blending, and it's all based on this concept of barycentric coordinates. So it's a big section of a class that is dedicated to the equivalent of how do you draw lines. It's how do you draw triangles, but you do so in a very specific way that gives you these nice mapping values. So that's what barycentric coordinates are. Questions? This slide is the key slide. When you're going to sit down and you're going to write code to actually make it rasterize a triangle, this is the slide that you come back to figure out what you need to write. It's that one special slide, you know. I was a student. I know that there are those slides in the lecture. It's like the one part you care about. It's this one. So if you're going to do triangle rasterization, this is your slide. So let's now move beyond the pixels and talk about transformations. You guys created a sprite class that allowed you to move sprites around on screen. You had a translate value. And we used the vertex program in order to apply a translate to each one of the corners in a quad. So what other transforms exist? Well, in general, there are three that are important in two-dimensional graphics. You have a translate, you have a scale, and you have a rotate. Being able to translate something means you can take a sprite that normally would have to be at the origin of the drawing system, and I can move it around inside the screen. So that allows me to move bullets around, allows me to move characters around. So translation's kind of the main one that you want. You take all of the input points, and you say the final position is equal to the initial position plus the amount that they should be translated. Where is the object in the scene? So now I can think of link as just a single point. Link is found at 0.2, 0.7. Link is found at 0.5, 0.5. And that one piece of data, the translate, is the one important part of where that sprite is. A lot of the time, though, you have some additional special effects that you want to apply to sprites. One that's used fairly heavily is scaling, being able to change the size of something. So you can take a character in a two-dimensional game and you can make him bigger, or you can make him smaller. This is often used for kind of cheap animations. Something kind of reverberates in size when it's destroyed, or when it's coming on screen. It can like start at a single point and kind of scale up to its proper size. It's like it's appearing. If it's done really quickly, it's an animation. And scale is also used when you need to have objects that are the same thing, but they're of different sizes. So you have multiple different spiders in your game, and you need to have spiders of different sizes to represent how mean and ugly they are. So scaling is used for that kind of thing. Rotations are also really useful to describe directionality. You can take a single sprite and you can rotate it in space to say where it's going. There are two ways to accomplish this. You can either use different images to show that the thing has rotated, or you can actually rotate the triangles on which they're being pasted. So who here knows about the Sega Genesis? You've heard of the Sega Genesis before. Sega Genesis was a 16-bit era console, the late 80s, early 90s. What was its main competitor?
Yes.
The actually wasn't the NES, it was the Super NES. The SNES, the Super Nintendo. That was its main competitor. There were others. You know what the main difference between the Genesis and the Super Nintendo was? The Super Nintendo could rotate, the Genesis could not. Sprites on the Super Nintendo had the ability to be rotated. So you could write Star Fox on the Super Nintendo, and you couldn't write it on Genesis. That was one of the main differentiating factors between those two systems from a hardware perspective. So it goes right to this stuff. Like, this is what people care about in two-dimensional graphics. So not only texture mapping, but also what additional capabilities do the sprites have. Rotatable sprites are helpful. You don't have to have rotatable sprites for the final project, but they certainly help. It's one of the ways that you can perform animations. So an interesting thing about transformations. You can think of them two ways. One is a set of equations that you apply to all of the input points in an object, whether it's a triangle, a square, or a polygon, or an entire mesh that makes up an object in a three-dimensional scene. You can think of them as being applied successively to each point. You can also think of them as the points don't move at all, you're moving the coordinate system. So notice here, this is applying the changes to the points. The triangle is the same in each image, but the coordinate system that is mapped on top of the points has moved. These are actually equivalent things mathematically. So you can either think of the points moving or think of the coordinate system as moving. And for most people, you're going to be like, no, that's weird. That's not the way that works. But it becomes surprisingly useful to think about the coordinate system moving rather than the points moving. And the reason why is matrices. So all three of these operations can actually be applied using a matrix multiplication. A translate matrix is applied by multiplying a identity matrix with the translate values in a third column. So I can multiply this by this, and this gives me x initial plus 0y plus tx. You'll notice that this matrix is the same as this equation if you multiply it out. With the scale matrix, I have sx times x, sy times y, and this third value 1. And with the rotate matrix, where I have x initial times cosine and y initial times sine, and this expression for y, I have a matrix that looks like this. Well, the equations are perfectly good. Why go to the matrices? I can make a piece of hardware that does this. I can have a piece of hardware that knows how to take 9 numbers and multiply them and add them together in order to apply them to a vector. Do you remember how to multiply 2 matrices together? How you kind of go along one row and then down the column of another, and that gives you a location in the result matrix. And you do that again, and it gives you the result, another result location. You remember this from linear algebra? Think about this in order to have a resultant vector. So these are equivalent statements. They do the same thing. But instead of now having 3 different pieces of code I need to write, or run, rather, now I only have 1 piece of code I need to run. And all I'm doing is changing the inputs. So I'm running the same code, but all I'm changing is the inputs. That should ring some bells about what we talked about earlier on in the class. Remember single instruction, multiple data architectures? Things that are highly parallelizable. They run the same code, but just have different inputs. That's this. So this is how it maps very nicely to GPUs with matrix operations. There are no ifs. It doesn't say if running translate run this, if running scale do this, if running rotate do this. It just does this for every operation. So when you hear about GPUs and the processing that they do, matrices come up all the time because matrices are really nice for packaging these. Also, from a math perspective, a matrix defines the coordinate system transformation. If you're saying you have a set of objects in this coordinate system and I want to know where they are in this coordinate system, a matrix is what describes that change, if you remember from linear algebra. A particular matrix is what the difference between two coordinate systems are. So now we're getting into that whole linear algebra piece and what coordinate systems are, and all of a sudden this idea makes a lot more sense. The matrix is the transformation from one coordinate system to another, and that's actually what you're doing. This is a change of coordinates. Translation is a change of coordinates, scale is a change of coordinates, rotation is a change of coordinates. They're all just change of coordinates. One more thing that we get out of this. Because of the way that we've constructed these matrices, they're what are called affine transforms. I can take three matrices that do a translate and a rotate and a scale, and I could even then do an additional translate, an additional rotate, an additional scale to say what I'm doing to a set of objects in the scene. So for example, let's say they have a file that has all the points for the Mac that's in front of you. And it is a set of 10,000 points that define the curved surface of the back of the Mac and all of the ports and all that kind of stuff. If I wanted to draw that one Mac multiple times in a scene, I would take those points, translate them, and put them on another desk, right? And then draw them over and over and over and over again. So I take one file and I can draw 30 Macs with it. So it's very common to do that in games. These pillars are exactly the same. I would just use 2 copies of the same thing. All the Macs are exactly the same. I'd use 30 copies of that. The desks are all the same. I would use 20 copies of those, right? So this is pretty common. And if I just have a rotated version of this, like one of these desks is just turned sideways, or the Macs are slightly adjusted one from another, I apply a rotate. Scale, not as useful for the Macs, but you can imagine how it could be used. So these are the common things that you need to do in scenes. Well, matrices can actually be combined, such that if I have a matrix of numbers and I composite them together, I'll get a single matrix that does all 3 operations in one matrix multiply. Just so happens that that's the way that this coordinate system works. So I can take the work that would normally require me to do 3 things and do it in one operation. So instant 3x speed up. So not only are these parallelizable, they also have a math basis that allow me to get an instant 3x speed up. As a computer scientist, that's all kinds of interesting to me, right? I want to make programs go faster. You just told me a way to make it 3 times as fast. Heck yeah, I'll do that, right? So here's the concept. If I have to do this 10,000 times, and I have 3 matrices, a scale matrix, a rotate matrix, and a translate matrix, and I have the input vector, the input point that I'm moving. So this is one point on the Mac. This is the position of this particular port on the back of the Mac. That's the thing that I'm moving. I can multiply it by the scale matrix to get the scale location, multiply it by the rotate matrix to get the rotated location. I know the scale matrix on the Mac will be scaled by 1. And then I multiply it by the translate matrix to move it into position in the scene. And I do that all 10,000 times on one Mac. Or I can multiply these 3 matrices together, get a single matrix, and do this 10,000 times. So instead of doing 30,000 operations, now I'm doing 10,005 operations, or 10,003, however you want to think of those operations. It's a 3x speed up. So that's another reason why matrices are used. All of this that I talked about so far is useful for just 2-dimensional operations. And it forms the basis of how we start creating these animated experiences. So sprite games give you the concept of something moving around on scene because each one of the scenes only differs a little bit. The characters have moved just slightly. If I have 1,000 things on screen and I move all of them between 2 frames, you won't recognize that those are movements of different objects. You'll just think they're 2 completely different scenes. But if I move them just a little bit at a time, that gives me the concept of something moving in a game. And each frame is related to the last. So I get that concept of object permanence because of the construction via 2D. Here's another example of a fooling of our brain. This semi-truck is carrying a huge bottle of beer. That's great advertising. Are there problems with this? Why does this work? In particular, if I sped up or slowed down on the freeway as I was driving by this truck that drew my attention, would it continue to look 3D? No, why not? The angles are wrong, right? It kind of begins to shift. So if I go forward, this one's going to kind of go more obliquely this way, and this one's going to go that way, and it's just going to look like a bent bottle, right? But at that one magic spot on the freeway, if I look at this, I'm like, whoa, that's a big bottle of beer coming out of the side of that truck. Well, this is exactly what we're doing, right? When we're trying to create a 3-dimensional program. I am taking a 2-dimensional screen, this thing is 2D that's in front of me, and I'm creating the concept that there's actually 3-dimensional objects moving around. It takes advantage of, number one, that object permanence idea. I move the scene just a little bit each time, so I get continuity. But I also have to create this 3-dimensional concept. It's all dependent on the viewer's position. So I need a set of math that allows me to describe where the user is in relation to the objects in the scene. So in addition to moving things around via these transformations, we'll have a couple of additional transformations. These are really easy to take from 2D to 3D, mostly. In order to have 3 points on a triangle that are in 3 dimensions, scale for z is the same. I just multiply by the scaling factor in z. Translating in z is the same. I just multiply by the translate factor in z. Or sorry, add the translate factor in z. Rotations are a little more complex though, because if I'm going to talk about rotating an object by some angle theta, what does that mean in 3 dimensions? So let's talk about these 3 transformations, then I'll cover the last one that makes it look like it's 3D, like the bottle concept. So how can I describe for this backpack, if it's this orientation is its regular orientation, what is this? How did I just rotate that object? How could you describe it? Was here, now it's here. So you could impose an axis saying that up and down there's some magic axis and that I have rotated about it by a certain amount, right? What if I rotate like this? I could describe some other axis that I'm rotating about that one, right? And to complete the set, what if I rotate like this? X-axis. Or you could call this the z-axis, and you could call this the x-axis, and you could call this the y-axis, and that would be fine too, right? We think in Cartesian axis terms. It doesn't have to be Cartesian, but you have 3 axes about which you could rotate an object. So if I have an object that looks like this, and I rotate it like that, how would you describe that? I rotated it like this, and then I rotated it like that. Is that a reasonable way of describing that rotation? Can all rotations be described that way? I can take a more complicated rotation and describe it in terms of 3 simpler ones? Sure can. Do the axes matter? Does the ordering matter? Gimbal lock. Yes, they do matter. But that's the concept. I can define some more elemental rotations and then compose those rotations together to make a more complicated rotation in 3D. So I can take these original matrices. They're actually 3x3 matrices, but they were being applied to two-dimensional data. And I can add one more column and one more row to them to come up with translation, scaling, and rotation. The rotation matrix is going to be a little bit more complex. The previous one was this combinations of sines and cosines. This one still will be a set of combinations. It'll just be more complicated. How much more complicated? Well, we can define 3 elemental rotations about the x-axis, the y-axis, and the z-axis. Again, you have to presuppose that these axes exist. And this is important in terms of the representation of the vectors that you are using in your program. But if they are Cartesian vectors, I can define these axes. And z-axis rotation is actually the same as the two-dimensional one I already had. I just add another set of columns and rows. I'm just doing nothing with the z values because I'm rotating about the z-axis. Well, x and y now fall fairly nicely where I just do that, not modifying the axis that I want to be rotating around. So those are my 3 elemental rotations. And if I combine them together, I can create a rotation about an arbitrary axis. It's a whole lot simpler rather than say, rotate this much around x, rotate this much around y, and rotate this much around z. I just say, here's a vector, rotate around it 45 degrees. So if I say there's this vector, here's the object, I can rotate about that axis. Or here's a vector, and I can rotate about that axis. So this is called the angle axis rotation. And I can actually get an angle axis rotation by using these 3 elemental rotations that are in my underlying coordinate system. So we apply alpha and beta. We rotate by negative alpha and negative beta, then rotate about theta, then rotate by positive beta and positive alpha. So we actually end out with a matrix expression that looks like this, which actually looks like this. And then you sit down and you multiply all those about, and you finally get the result matrix that is what you want. So this MMMMMM thing is the result of doing this multiplication. One way of forming it. And then you hand it to a math person or a computer science person, and they trim it down and try to get it to the smallest number of operations they possibly can, and you actually get this. But that's the concept. So that's rotation in 3D. What's really interesting is that this rotation has a lot to do with flight dynamics, how a vehicle in flight moves. You've heard of yaw, pitch, roll. Yaw, pitch, and roll are just one formulation of this. This is called proper Euler angles, ZXZ, because I chose to rotate about the z-axis and the x-axis and the z-axis in order to get what I wanted. But there are 11 other options in order to do the same thing. And yaw, pitch, roll uses the z-axis, the y-axis, and the x-axis to do it. It's the Tate-Bryan formulation, ZYX. If you want to look that up on Wikipedia, feel free. So how are we going to use this? What's the code? Well, we're going to use it like this. This is a set of vertex and fragment programs and the associated CPU side code in order to create a matrix and then multiply that matrix by the input position. So I have a vec3 that comes in for position, or vec2 if you wanted to use a two-dimensional data, and I multiply it by model view, which is defined as a mat4, which is a 4x4 matrix. So 4x4 matrix times vec4 gives me GL position. And that's my program. The other transformation that we need in order to create 3D is the fact that we need things that are further away to look bigger. As something, or sorry, smaller. As something gets closer to you, it gets bigger. As it gets further away, it gets smaller, right? That's something we still need to capture. What we've been doing so far has been what's called an orthographic projection. We didn't have any Z. There was no Z. If something was 1,000,000 miles away versus right in front of my face, it was the same size. So an orthographic projection defines a box. Everything that falls inside that box ends up on screen. A perspective projection defines a frustum. A frustum is a pyramid with the top chopped off, laid on its side. Everything that falls inside the frustum ends out on screen. So there's some math behind this. I'm not going to go over it. It's referred to as the projection matrix. You can use a matrix class to get the projection matrix. If you're really interested in mathematics, go ahead and look it up. But in general, the points that you are manipulating in your vertex program follow something that looks like this. You have a matrix that is used for moving the model around and positioning the viewer in the scene, called the model view matrix. You have a projection matrix that does that, make things look smaller as they get further away. And then you have the viewport transform that actually takes values that are in the -1 to 1, -1 to 1, -1 to 1 coordinate system and makes them be in pixels. So the cool thing about this, you have points that are coming into your program that you can look up in your debugger, and it actually says what points you're handing off to OpenGL. If you know what matrices you're handing to OpenGL, you can whip out a piece of paper and a pencil, and you can multiply the matrices by those input vectors and come up with pixel locations of where those points are in the output raster. So I'll have some point, 1, 2, 3. I'll run it through these matrices, and it will say that point is found at pixel 4875 in my output image. So this is the whole enchilada, the whole shebang. You can actually do this on paper and find out what these are using these matrices. So in our current program, we don't have a projection matrix, and our model view quote-unquote matrix is actually done using a shader. The viewport transform you supply to OpenGL using the GL viewport call that tells it how to map its coordinate system to the image. You can also split up the model view matrix into 2 matrices if you want to. This is typically not done on the GPU. This is done on the CPU, where one is to show where the object is in the world, and another one is to say where the user is in the world viewing the rest of it. This is how you model the world. Instead of moving the user around in the world, you move the world such that it is where the user is. So the user is literally the center of everything. The user is always found at the origin. So use a lookat matrix for this. Anyway, so those are all the matrices. Here's the actual implementation of these matrices from the OpenGL implementation. There's a camera matrix, orthographic projection, perspective projection, viewport transform, and there's all the typical matrices for actually working with a program in 3D. Here's a program that separates the projection matrix and the model view matrix. You notice that it's projection times model view times vec4. You want to talk about texture mapping, using barycentric coordinates to actually map a texture onto a triangle. You specify locations U and V in the image, where this position on the image gets mapped to this point. This one could map here, this one could map here, actually. So here to here, here to here, here to here. These ones in the middle are blends of these 3 locations using barycentric coordinates. And that's how it knows to look up this pixel when drawing that pixel. That's how the texture 2D function works that you used in the last lecture. So we can use OBJ files and triangle fans in order to do rasterization. You can run length encoding for this. One way of doing the mapping. Here's some equations for lighting if you want to do three-dimensional lighting. And that was half of a semester from CS 4600. So it's a lot of information. But it is all of that information in one slideshow. Kind of gives you places to look. This is a fairly simplified functional set of shaders for three-dimensional graphics using model view matrix, position matrix, normal vectors, one light in the scene, and texture coordinates. So pretty much every game written from 1990 to 2000 used this. And even some games after that. So I thought it was useful stuff. So you can write all that custom stuff yourself and have it be performant and wonderful. Or you can actually use a class that Apple wrote. Apple wrote what's called the GLK base effect and wrote a set of shaders for you and wrote a support class. This allows you to have up to 3 lights in a scene and 2 texture stages. And it's an object-oriented set of structured input data in order to work with OpenGL. So you use the GLK base effect and the OpenGL library in order to do three-dimensional graphics and implement everything that I have in this slideshow. So there you go. Look up GLK base effect. It'll generally have the things that you need. Let's take a quick break, and let's actually see how this applies to the code that we wrote last time. Because that was a lot of information. Let's do some of that. Okay, so let's look at sprites from last time. And we're going to apply additional two-dimensional transformations. With the way that I'm defining this, you can also take your sprites and you can even add a z direction to them and create what's called 2.5D, where you have flat objects, but they can rotate in 3D. So we'll write the two-dimensional piece first, but the three-dimensional extension to it is rather natural. So I believe this is code from lecture 22, whatever code was what you wrote last time. So here's your program from last time that had Mario and me. I made a slight modification because Kevin had a horrible picture of me for one of the sprites because he's a jerk. So we've got Kevin instead. I'm much nicer to Kevin. He's in a suit and everything. Okay. So what we want to do is here in your current vertex program, you're only applying a manipulation with a translate uniform. Your sprite, however, has definitions for a scale and a rotation, but we're not doing anything with them. So if I were to go to your sprite view controller and take Mario and say Mario.scaleX equals Mario.scaleX plus 0.01, he should get bigger in the x direction, right? That's what we want to have happen. So every frame, he would be 1% fatter. But alas, Mario remains his thin self. So how do we implement that? Well, if we look at the sprite definition, we have a variable that defines the scale in x, and it's initially sized at 1.0. Scale should start at 1.0 because if you scale by 0, something becomes infinitely small, right? That axis is completely collapsed. So scale of 1 is actually the proper default value. But we're not actually applying it. So we use the GL uniform calls to take the position x and the position y and store them in the translate variable in our shader. What we want to do is do that with the scale component as well. So we want to take scale x and scale y and put them in a vec2 called scale. So if we go to our vertex program, here we have the translate uniform that is a vec2. We want to create another vec2 called scale that takes on the same values as scale x and scale y from the sprite class. So how do I use this value? How I can has code. Someone help me. If this helps. Write my codes. So here's scaling. Right now we have translate doing this. Come on. I hate this window size. So position final equals position initial plus translate x. So position final, position.x, is position initial plus translate x. That's what we're currently doing. So if I didn't care about translations, how would I scale? What's the code I write? going to wait till somebody answers. That may be too small. This is the code that I currently have. The x position equals initial position plus translate. And I need that one. X final equals x initial times scale. Help me out here. What characters do I write in here to do that?
Maybe just translate the scale.x.
Well, there's a multiply. There's no add. But yes. So this would do nothing. How do I get this effect? Using this value. This is not a trick question. Multiply by scale.x. Yep. Ask too many quick trick questions. I've really got you guys in kind of a hair trigger. I'm sorry. That's my fault. I'm going to stop asking so many trick questions. Look, Mario's getting fatter. He's actually changing in size in Y. I wasn't expecting that to happen. Why is that happening? Oh, because it's scale X, scale X. There was a copy-paste error. Well, that tells you about uniform scaling. If you scale by the same value in both X and Y, it just gets that much bigger. There we go. Now Mario is eating way too much Italian food. So there's my scaling. But he stopped moving, right? Because now I'm not paying attention to translate. So I don't have a slide for how I combine these two together. But I had position.x plus translate.x, and now I have position.x times scale.x. How do I do both of these? I'm going to need an add, and I'm going to need translate, but where do I put them? Well, let's just try something and find out. What should I type? Let's just try a thing. It doesn't have to be right. What should I try? Do a times and then do an add? Like that? Great. Let's see if that does what we expect. So now we should be seeing Mario both getting fatter as well as moving up, right? That's what we're hoping to see. And that appears to be the case. Mario is moving up, the others are moving down. I know that I'm only making Mario fatter, but his head is getting further and further up. So I do know that he is moving up and he is getting fatter. So yeah, this is correct. Well, but I also could have done this, right? Just changed the order of operations. So which one is correct? So all I did now was add to the position before I scale. Just change the order of operations. So it looks like it's still working. Let's see if we can see a difference here. Make this go a little bit faster. In fact, let's do this. Let's have everything move at the same rate, but let's also have it scale in Y. This is not going to show what I want to show. So I'm short on time. The order of operations that is what you probably were expecting is that all it does is change in scale, but it still moves at the same rate. If I perform the order of operations like this, I take the translate amount, if I want to translate by 3 units up, and then I multiply the scale, say 2 times as large, I'm actually translating by 6 units. So I don't want to scale the translate. I just want to scale the object and then translate it. So the proper order of operations is scale first, then translate. I can use it like this. This is a perfectly valid formulation. It's just not what I intended. So the simple one is actually the right one. Cool. So one more question. How do I apply this one? That one has more characters to it, but I combined this one and this one by just choosing the order of operations. I should now be able to combine this one by just choosing the order of operations as well. Let's start by just writing this and making sure that it works. So x final, the x position of the x component of GL position is position dot x times cosine of rotation, which we need to bring in as a uniform, minus position dot y times sine of rotation. So that's the first component. And if I copy and paste that for the second component, and my editor really, really wants to do whatever it's doing right now. So this is position final is equal x initial times sine of theta plus y times the cosine of theta. And I need to define theta. Uniform, a vec1 or a float. Oop. Rotation. So I need to bring in this value. So I go to the sprite. I use a GL uniform 1f call, passing in the rotation property here. So this rotation property you guys had written previously, it's just a property var rotation, which is a float. And so let's see if we can get Mario to rotate. Cool. So it's working, right? It's doing what we want. It's rotating counterclockwise. And it looks like there's something kind of strange going on with Mario. He's getting shorter. But it is doing something correct. We'll talk about the him getting shorter piece here in a minute. I don't have very much minute. But let's finish this piece off. That's the rotation. Now I need to apply the other two, but I need the correct order of operations. What order of operations should it be? What do you think I ought to be doing? Should I rotate, translate, scale, scale, translate, rotate? Some other combination of that? What makes sense? Before I needed to avoid scaling the translate. Here I need to avoid scaling the rotation, such that if I rotate by 45 degrees and then scale by 2, I don't want to rotate by 90 degrees. So how do I guarantee that?
So do you want to multiply by the scale first, then
Yep.
do the rotation stuff?
So you multiply by the scale first, then do the rotation, then do the translate?
Yes.
Yes, probably. Maybe you want to do the translate before or after that, but certainly the scale needs to be first. But yes, usually you rotate and then you translate, because rotations happen about the origin. If I translate first and then rotate, that means that I move Mario away from the origin and then rotate him on a pinwheel centered at the origin. That's probably not what I wanted. I want to rotate Mario at the origin such that he rotates about his center and then move him into the world. So the proper sequence of events should be scale, then rotate, then translate. Again, it doesn't have to be that way, but that's the way that most people think of it. In fact, if I want to rotate about something that is not Mario's stomach, I would do a translate first. So how do I scale first? Well, I need to multiply it by position, but position x is actually found in multiple locations in this equation. So multiply by scale, and everywhere where I see position x, I just stick that in there. And same thing with position y. Now I need to translate last. Addition happens after all the adds and subtracts and all that, so I can just do it at the end. So if this is right, I should see Mario rotating and changing in size and moving. That does appear to be occurring. If I go back to what I'm actually telling it to do, let's just have it translate mat 1 and mat 2, where mat 1 is Kevin. Great. So Mario is getting taller because I changed it to scale Y. There we go. Now we have a program that supports translations and rotations and scales, which is good because you probably wanted that for the final project. So you could have enemies of different sizes, and those enemies could be rotated to be able to follow their direction of movement, right? All useful things. So how do I make this be a matrix? Because I really want to talk about this last point, even though we're out of time. Well, I can replace this entire set of equations with just GL position equals vec4 of position dot x, position dot y, 0, 1, and multiply that by a matrix. So I can bring in a uniform of type map4, usually called model view. So I don't need those uniforms, don't need this calculation, and the way that I multiply the multiplication is just that. And GLSL knows how to multiply a matrix by a vector. It's just part of the definition of the language. And so this does that, except for it's doing it in 3D. So it does wherever my 3D expression was. I don't know where it went. There it is. So it's doing this operation. So the way that you bring in a matrix is, instead of calling GL uniform 2F, you call GL uniform matrix 4FV. And here you're passing in the location of that, which is model view. It's called a matrix 4FV because you can actually bring in multiple matrices, and they only have one call for some reason. The count is 1. I'm sending in one matrix. Don't want to transpose it. and the values that I'm passing in are just an array of float. This is an unsafe pointer to GL float. I think this is GL false. Anyway, you can look that one up. But that's how you send in the uniform. So it's 16 floats you're passing in. Well, where do you get those 16 floats from? There's a nice class called GLK matrix 4. And I can ask for matrix.m. This is an array of 16 floats. And so look up the GLK matrix class. You can define rotation matrices, you can define scale matrices, you can define translate matrices, and you can do matrix multiplication with the class. So you're doing all those calculations on the CPU, and then the work that is actually done on the GPU uses this hardware accelerated multiply. So it actually does this operation in 1 clock cycle. So let's do a comparison here. Actual number of operations. Here I have for each point, I have 1, 2, 3, 4, 5, 6, 7, 8 multiplies and 4 adds. I know there's a negation in there, but those are basically free. So 6 multiplies and 4 adds. Versus how many multiplies and adds are there when you're doing a matrix versus a vector? Because I do matrix 0, 0 times vector x, matrix 0, 1 times vector y, matrix 0, 2 times z, then the last column, 3 times 1. That gives me the first element of the result vector. Then I do that again, that again, that again. So it's 16 multiplies and 12 adds. So why is this better? If this is 6 multiplies and 4 adds versus 16 multiplies and 12 adds, why did we go to the trouble of putting it in matrices? Well, because there's a piece of hardware that does this in 1 operation. So this is 1 multiply. So right there you get like a 12x speed up, right? In addition, what's this? Cosines are really expensive, really expensive. It's like 30 multiplies and a bunch of stuff. And I'm doing it 4 times. So this is the equivalent of like 100 operations versus 1 operation. This is 100 times faster, order of. Yes?
Sure. This is the compiler smart enough to optimize those down into just 2, 1 sine and 1 cosine?
The sine and cosine? Maybe. But it's still doing it at least once. And there's no reason to even do it if the rotation value didn't change, right? So if I'm playing the game of games, the best of all, A Link to the Past, there are very few rotations that happen in this game. Most sprites don't rotate. That's all kinds of waste, right? There's no reason for that. If I'm playing Star Fox, there's way more rotations. But A Link to the Past doesn't use it. So you're talking about order of 100x speed up by doing a little bit of work on the CPU to pre-compute some of your values. That's still better. Anyway, so that's why that's important. Not only are we getting the advantages of single instruction, multiple data, and being able to do matrix operations in a single GPU operation, we are also highly parallelizing those operations. So you're getting huge benefits. With this particular program, the number of things I'm running through OpenGL right now is 12 points. 4 points per sprite. If I'm playing a game like Robokill, where I've got hundreds of sprites on screen, I'm on the order of 1,000 to 2,000 things. Probably not that big a deal. You could do this and it wouldn't be a problem at all. You don't need to work with matrices for the final project. But when you're talking about that from a systemic point of view, where you're actually planning on this being the workhorse for your application, this is the center of all of the loops. For all of these things, for all of these things, for all of these things, do this. This is the most important part, the hottest spot in your application, it's the most important part to optimize. So you look into this problem pretty carefully. And in 3D, this very much becomes a problem. Because in 3D, rotations are way more complex, right? The 3D rotation had tons of sines and cosines in it, because it was this, right? So you optimize this, you build the matrix once, and then you draw the object many times. So that's where you get those massive, massive, massive speedups. Not only parallelizing, but you're also pre-computing. So thinking about it in terms of a change of coordinates rather than a modification of multiple points, and organizing your code in that way allows you to gain these huge speedups. Doesn't matter as much for your program, but I just couldn't help myself. It's an important thing to talk about in terms of graphics. So take it where you will. When you start going to three-dimensional graphics where this actually matters, look at doing that. For now, this works just fine, and you can turn that in for your final project. You know, this piece of code allows you to do rotations and scales and translates without having to use any matrices. So there you go. So I'm going to get rid of this matrix stuff. We're just going to use the straight up uniforms. Make sure that this code actually works. And many of you are doing the default final project. One piece that we didn't handle was even if I'm not rotating Mario, he gets shorter as I rotate him. It'll be easier to see if I just rotate Kevin. In fact, let's not even draw these. Rotate. Oh. Don't change in position. All you're doing is rotating and just drawing Kevin. I want to make Kevin dizzy because he had that bad picture of me in the last lecture. So notice that it's changing in scale. Kevin's a thin guy, but he's looking kind of fat in some of those rotations. Why is this? In fact, it'll get even worse if I add this default image and get rid of the bars. If I slow it down, you'll be able to see it even more. But this is an aspect ratio problem. It has to do with the fact that we're trying to draw a square, but the screen that I'm drawing it on is not square. Because OpenGL always maps to -1 to 1 in X and -1 to 1 in Y, right? So if I rotate it, it's going to change in shape. It's going to actually shift as it rotates. So how do I solve that problem? Well, I need to have it not map from -1 to 1, -1 to 1. I need to have it map from, say, -1 to 1 and -0.6 to 0.6. Or have it map from -1 to 1 in X to 1.4 to -1.4 in Y. That's what I need to do. I just need to change the mapping. The way that that's accomplished is using the GL viewport call. So here you say what mapping you want for X, Y, width, and height. Unfortunately, I'm out of time. I'm going to have to leave it up to you guys to make this change. But essentially, you pay attention to bounds.width and bounds.height. And you change it such that in one of the directions it maps from -1 to 1, but in another one of the directions it maps to that times the aspect ratio of the view. So this is not super easy, but you'll want to do it because as you rotate things, you don't want them to get fatter and thinner. but it just changes your assumption that this is -1 to 1, -1 to 1. Such that when you draw a square, it should be a square. Whereas right now, before it was rotating, we didn't notice, but we're drawing a square, but what ends out on screen is actually a rectangle, and that rectangle, notice, has the same aspect ratio as the screen. So if you're drawing this, and you've applied the viewport called correctly, this will be a square. Okay? I give you your direction for what you need to do in order to fix the problem. I'll have to leave it at that. So I'm going to do a thing that I never do for you guys because this final project is something, this code is essentially required for the final project. So I'm just going to start up here at the top of this file. And I'm going to scan very nice and slowly from top to bottom. And I figure that will be useful to some of you as you're doing your debugging. Do not type in each one of these characters one after another into your IDE. I don't want you to do that. I'm doing this for debugging. So you can see how this is done here and compare it to your own code and see what the differences are. So you can figure out what's going on. So there's sprite.swift. Here's sprite viewcontroller.swift. And here's the app delegate, which should just be that piece. Here's vertex.glsl. We don't need the model view matrix. And here's your fragment shader. So I have uploaded the code. The reason why I'm not giving you a file that contains the code is because I want you to write the code. This is a debugging tool. We clear? All right. Hopefully this will be helpful to you who are working on the default final project for class. This little sprite system is so much easier to use than any library that you would bring in that has similar features. It's much, much, much better formatted. And you guys actually understand it inside and out. And so I think it's a much better way to talk about games. I know it's taken us a while to build up to here. For some of you, this is incredibly interesting. I understand that for some of you, this is just a pain. And you think, oh, I hate OpenGL, I don't want to use it. It's not easy to use, whatever. I want you to learn something from the class, and I feel that it's valuable. And that's the reason why we've done this. And I hope that if you can't like all of it, you can at least appreciate that. Anyway, we're done with OpenGL. We'll be moving on to other topics.